The story of the lithium-ion battery begins in the 1960s and 70s, when scientists explored how lithium could move between materials to store energy. In 1976, M. Stanley Whittingham built an early version, later improved by John Goodenough and Akira Yoshino in the 80s, and that created the first rechargeable, safe lithium battery. Sony commercialised it in 1991, but mainly for cameras and laptops. And lithium-ion first powered a vehicle in 1998 with the Nissan Ultra, but it took another decade for Tesla's Roadster to really launch the modern EV era. And since then, lithium-ion batteries have transformed. Costs fell from $800 per kilowatt hour in 2013 to under $100 per kilowatt hour today. Energy density has more than doubled, and the average EV range tripled from 80 to nearly 300 miles. And yet, we're just getting started, with energy densities expected to roughly double again within the next decade. But when it comes to talking about battery development, it's very difficult not to talk about China. After all, it produces about 3/4 of all lithium-ion batteries, controls 70% of global cathode capacity and 85% of anode production. It manages 2/3 of lithium refining and 93% of graphite anode materials. It also holds a near monopoly, over 95% in fact, on key precursor and LFP cathode materials. So with China quite literally leading the charge, is there still room for innovation from, well, little old UK?
Our 3 free YouTube channels on EVs and clean energy tech are funded by our fun-packed test drive-tastic events in the North, West and Greater London, and our events down under. Next up, Everything Electric Sydney 2026. Plus, check out everythingelectric.store for merch and much more.
It turns out that yes, there is room for the UK, and its real influence lies in generating a staggering amount of battery IP. The Faraday Institution and UK Battery Industrialisation Centre, or UK-BIC, have been key to the UK's battery ambitions. The Faraday Institution drives research on next-generation chemistries like solid-state, sodium-ion and lithium-sulfur, whilst also focusing on sustainability, aiming to recycle 95% of EV batteries by 2035, and of course, exploring second-life energy storage. UK-BIC bridges research and industry, scaling lab breakthroughs to gigafactory level production and developing the skills needed for a resilient UK battery sector. So across the battery value chain, from materials and refining to cell development, manufacturing and storage, UK companies are finding ways to squeeze even more energy and reduce costs from these cells powering our electric future. On the materials side, the UK is seeing some exciting stuff and a bunch of companies all focused on pushing the boundaries of battery performance, safety and sustainability. In Cambridge, Niabolt is developing a proprietary anode that enables ultra-fast charging 0 to 80% in under 5 minutes without degrading the battery. Also in Cambridge, Tyson Nadel is developing a novel polymer electrolyte for sodium batteries. And in Oxfordshire, Nexion is creating next-generation silicon anodes to boost energy density, increasing range whilst reducing size and weight.
In Bristol, Anaphyte is reducing energy use and emissions of battery cell production. Its dry coating precursor technology combines all the key electrode ingredients into a single engineered material, enabling high-speed dry coating at scale. But what is dry coating and why do we need it?
So the normal way that lithium-ion batteries are made, the most common way, which has been the same for about 20 years, probably even more than that, is you take a piece of very high tolerance, essentially kitchen foil. It's not kitchen foil, obviously. And you coat it with a slurry which is kind of, imagine you want to put paint on a wall. You mix the pigments in with the liquid, which could be any kind of solvent. You paste it on the wall, and then you let it dry. And then when it dries, you're left with the pigment stuck to the wall. You're kind of trying to stick electrode material, so battery materials, NMC, LFP, things like that, onto a foil and then remove the solvent. So if you have it's a bit like, I don't know if anyone's touched kinetic sand before. It's not exactly the same as that, but it's that sort of thing where when you touch it, it crumbles. But when you apply any kind of pressure to it, it becomes like a film, a flexible film. So dry coating, you're taking essentially a crumbly material, you're pressing it between rollers, and then you can form the electrode without needing the solvent. And that reduces the need for that huge energy, capex intensive oven. And then you can significantly drive down the cost of the production of the battery.
Those battery materials eventually make their way into cells, and the UK is showing real innovation here too. In Southampton, Ilika is developing solid-state batteries with ceramic electrolytes for safer, more energy-dense EVs. In Sheffield and Lancaster, Faradion and Lena are building sodium-ion batteries using cheap, abundant and safe materials. And we recently featured 11 Energy, which are using sodium-ion cells for their home battery systems.
But building the physical cell is only half the battle. To truly unlock performance, we must understand what's happening inside and at a microscopic level. The UK is leading the shift from physical trial and error to digital precision. Two London-based companies, Breathe Battery Technologies and About Energy, use physics-based modelling and intelligent software to design better batteries more efficiently and manage them on the road. And I recently visited their facilities.
So at Breathe, we produce Breathe Design, a cell design software tool, Breathe Model, a simulation tool, and then also Breathe Charge, an embedded software that helps organizations to get the maximum value for money out of the battery system they've installed in their product.
So what we do at About Energy is we help pack designers turn cells into battery packs. That starts for us as a relationship with the cell manufacturers. So we're now becoming the world's independent third-party verifier of cell technology, where cell manufacturers send us the latest and greatest cells. We turn them into digital models. And then when somebody comes to designing a battery pack like McMurtry, they use our software and our database to evaluate all the different cells in the market, but in a digital environment, rather than having to get sent physical samples.
Industry leaders are already deploying this technology. Breathe is working with Volvo and Oppo smartphones, while About Energy partners with Mercedes, Porsche and McMurtry. But why is this necessary? After decades of use, surely we already understand how batteries perform.
So the way battery charge management has been carried out for the last number of decades is that very smart engineers in organizations all over the world are using either empirical methods in a laboratory like this or offline simulations to simplify the battery system and its electrochemistry down into a small number of values that are codified in a table that's typically called a lookup table that then gets embedded in the application, and that's used to define the charging strategy. And the massive limitation and drawback of this is that that table is static and it's baked in for a particular point in the lifetime of that battery, and it can't evolve as the materials degrade and that battery itself evolves as it's used by myself, my friends and my family in many different ways throughout its lifetime. What that means is that we all experience an underutilization of what that battery hardware is capable of.
To build the physics-based models, Breathe and About Energy need to interrogate the physical cells and test their own software. This is how they do it at Breathe, which also happens to be home to London's largest battery lab.
The battery cells then come in here, where they undergo the material analysis to assess the parameters that feed those mathematical models that describe how those battery cells are operating. But the other thing that happens here is that small cells are generated, which can then go through various different test cycles. So through different charging cycles, through different temperature profiles, etc., etc. So actually those mathematical models can be really tested and optimized across those wide range of operating conditions. This is not a fridge, but this is in fact a way to test the validity of the software that's being developed here. So there are a load of EV battery cells in here, which are between two clamps to simulate the compression that they'd experience within an electric vehicle. And then go through a number of different cycles to sense check what is actually happening in the battery and comparing that to the software model. So that constant calibration can happen. So Breathe Battery Technologies knows completely how representative their models are.
So what do the digital twins mean in reality for everyday people like you and me?
And what that translates to in our hands then is, in the case of Volvo and their ES90 vehicle and their single technology stack that relies on Breathe Charge for the charging strategy, it's 30% faster charging in a sort of nominal environmental case, and even as much as a 48% reduction in charging time in a low temperature environment, but a more nuanced set of benefits for the end user that include just overall a more consistent charging experience as the battery ages, degrades along different degradation pathways. And then for our customers in the consumer electronics space, with a different calibration of the same product, they're able to realize enormous increases in battery lifespan. In the case of Oppo, as much as double the battery life to create a product that is more sustainable and really delivers then much better return on investment when you and I spend.
So today, batteries are really expensive. Like a battery electric vehicle the battery pack is about 30 to 50% of the bill of materials cost of the car. So on the whole, batteries are really, really expensive. What using digital simulation and tools allows you to do is, number one, reduce a lot of the physical prototyping and testing to drive down the development cost. But also using simulation, you can run millions of different design variants and get to a more optimal solution. So you can actually take your battery pack and reduce it in size by around 20% using digital simulation. So the benefit to the end consumers is hopefully cheaper electric vehicles, cheaper products that last longer and that are using much newer technology.
Reducing battery size, improving charging, and extending battery life. What's not to love? But for car companies, there are even more wins if they can continue to close the cell knowledge gap.
So we recently started working with McMurtry, who are developing their new McMurtry Sperling car, and they needed to accelerate the development of that car. New cells are coming to market all the time, even from their partner Molicel. So what we help them do is turn that latest cell into a digital simulation model, so they could iterate through that virtual design much more rapidly than in real life. And that saved them 7 months of development time and reduced the time to market for that car for 70%.
Modelling cells is difficult because batteries are a closed system. You can't see inside without breaking them. But another huge challenge is temperature. Governed by the Arrhenius relationship, a cell's performance changes exponentially with heat. To model that accurately, you can't just use a standard thermal chamber. You need extreme precision. And About Energy has a unique way of doing it.
Pretty much everybody else does in industry is use something called a thermal chamber, where you put the cell in a little rig like this, and then you control the air temperature around the battery. But as soon as you start charging and discharging the battery, it heats up. So when you collected that data, was the battery at 25 degrees, your air temperature, or was the battery at 45 degrees because it started to heat up? So what we do is we use these things called Peltier elements, which I'll show you in a second, and copper plates. So we basically put the battery in here, surrounded by thermal gel, with a precision thermistor in on the surface of the cell. And this copper plate allows us to basically control the temperature of this battery really precisely. So we control these copper plates' temperature with these things called Peltier elements. And these Peltier elements are the most incredible little devices. I only heard about them when I started my PhD, but they're a little solid-state heat pump. So if you pass current one way, one side gets hot and the other side gets cold. And if you reverse the current, then the opposite happens. So you can heat and cool very precisely. And in my PhD, I developed a temperature controller. It took me about 2 years to build. We had all these PCBs. I had to learn how to design PCBs, and it ended up being about 10,000 lines of code. But that controller is basically a really low-cost Peltier element controller that heats and cools the battery 30 times a second. And with this setup, we can actually get the battery down to as low as minus 40 degrees, and we can go up to like 120 degrees. Wow. So this system allows us to collect really accurate data on the batteries.
By understanding the physics of the cell at a microscopic level, we can unlock massive gains in performance, cost, and development time. But the UK's battery ecosystem isn't just looking at the single cell, or indeed even just cars. It's applying that expertise to the grid itself.
And when it comes to energy storage, the UK's ecosystem goes far beyond just home batteries. Banbury-based Ionetic is accelerating industrialisation of custom battery packs to exact specification for various electric vehicles. And at the grid scale, Invinity Energy System leads with vanadium flow batteries, which are known for their durability, non-flammability, and built to last 25 years plus. Perfect for long-duration energy storage. And Highview Power takes a slightly different approach with liquid air energy storage, providing days of backup power to tackle renewable intermittency. And Zenobē, Ally and Felton all repurpose Second Life batteries for stationary storage and grid flexibility. Despite British Volt in Blyth sadly not going quite to plan or doing any wonders for confidence in UK Gigafactory capability, there are actually a number of other Gigafactories already up and running, under construction or still in planning. In Sunderland, Envision AESC is expanding its site to supply Nissan with next-generation EV batteries, growing from around 2 to nearly 16 gigawatt-hours a year. Down in Somerset, Tata's Agratas Gigafactory is under construction, a £4 billion project that will power Jaguar Land Rover's electric future when it opens in 2026. In the Midlands, there's strong momentum too, with Eve Energy and Volklek both planning new large-scale sites. And in Scotland, AMT Power is developing a smaller mega factory focused on high-performance cells. And if these all go to plan, this will be a significant chunk of the anticipated 140 gigawatt hours total capacity that the Faraday Institute predicts we'll need by 2040. The UK also has tremendous opportunity when it comes to battery materials, and not just mining, but also refining, processing and recycling. We've got lithium potential in Cornwall with Cornish Lithium and British Lithium, a new lithium refinery in Teesside, the world's largest specialty graphite production, Europe's second largest nickel refinery, and low-carbon aluminium smelting. And companies like Altilium and EMER are rebuilding recycling facilities to recover lithium, nickel and cobalt from old batteries. In fact, Altilium's Act 2 facility in Plymouth recovers over 95% of cathode materials, aiming to supply half of the UK's critical battery metals from recycling by 2040. And by turning raw and recycled materials into high-purity battery-grade components, the UK can keep the value of those materials and generate a secure and circular supply chain. So no question, there's plenty to be excited about. But the original lithium-ion battery is a cautionary tale. In the 1980s, Professor John B. Goodenough and his Oxford team invented the high-voltage lithium cobalt oxide cathode, which doubled energy potential and made modern lithium-ion cells possible. And the UK even held the patent through the Atomic Energy Research Establishment. But the UK failed to commercialise it. The university initially refused to back the patent. The inventors received no royalties, and Sony eventually combined Goodenough's cathode with a carbon anode to create the first commercial lithium-ion battery in 1991. The lesson? Innovation alone isn't enough. The UK needs to be smart with its IP to lead the next generation of EV batteries, from solid state to sodium ion to the coveted 500 watt-hours per kilogram. That is all that we have time for. Let us know what you think in the comments. Please do like and subscribe, and if you have been, thank you for watching.